So we have talked about the fixed and the random effects and some intuitive criterion for choosing a fixed and random effect when you fit the model, and something about degrees of freedom as a difference. So here in the document, it's the same document that I was using for the last video for the astral measurement one-way ANOVA simple example, and you can find this document on my personal website. There's a link. So I screwed down a lot, I jumped a lot, and just quickly to this page with a formula that I want to show here. That is this formula XXX. Okay. So I'm going to introduce to you the difference between fixed and the random effects in terms of the estimate size. So you see that when we fit a fixed effect model, right, we used up a lot of degrees of freedom depending on how many covariates you have. And if you feed them as random effects, we save that degrees of freedom, so we only lose 1 degree of freedom for fitting the variance component for the random effects. And it seems nice, so the random effect model can do a lot. We can fit any number of covariates basically, and we just use 1 degree of freedom, which is really cool. But there's a price to pay for doing so. The degrees of freedom that we saved are not really free. And the most important price to pay here is the unbiasedness of the effect estimate. So if you're familiar with the statistical theory for linear models, that in a linear regression, when we estimate the fixed effects, the estimates are usually called BLEU, or best linear unbiased estimates. That basically says the estimate we get from the fixed effect model is unbiased. The expectation of the estimate is theoretically the same as the true estimate if the model is correct. But this nice property is not guaranteed anymore when you fit a random effect model. Depending on the situation that you have, you will end up with a bad or good estimate compared to the fixed effect model. So if you look at this formula here, all right, this is this simple one-way ANOVA situation that we showed last time, and on the left-hand side is the random effect estimate. It's UI hat. On the right-hand side, you have a long thing here. And in the last bracket, we have yi bar minus mu, which is the person's mean or the group mean minus the overall mean. So this is the fixed effect estimate or the unbiased estimate for the difference between a person's mean or the group mean and the overall mean. Okay, so it's obviously theoretically there is a difference between the random effect estimate and the fixed effect estimate. The difference is a coefficient that we times here. So there's a sort of a fraction or some coefficient in front of the fixed effect estimate that give us the random effect estimate. And this ratio is something between 0 and 1, because you see we have variance component here, n is sample size larger than 0, 1 is larger than 0. So the numerator is n divided by sigma square, the denominator is n divided by sigma square plus something else. So this is a value between 0 and 1. So depending on how close this ratio value is close to 1 or 0, we know how much difference or how much deviation we have comparing the fixed and the random effect estimate. So what determines this ratio? So in this ratio we have the two variance component estimate and the sample size. So these are the sort of criterion that gives, or the estimates that determines such a difference. So first of all, let's look at the sigma u square here, right? So if sigma u square is big, then 1 over that is small, and 1 over that again is big. That basically tells you if the variance captured by the random effect is big, then this ratio will be close to 1, and the random effect estimate will be close to the fixed effect estimate. That means we have more information in the random effects, so that we don't have so much difference between the fixed and random effect estimate. And another thing is that the sample size. So this is a 1 over sigma u square here. This is a sort of like a relative sample size to the random effects. So basically, if you have more samples or more observations, they have more information about all the estimates, then the ratio will be close to 1, and the difference between the random and fixed effect estimates will be not that big. If you have a lot of random effects, not so many observations, then you don't have much information to infer the random effects, then the difference between the two estimates will be bigger. So the ratio will be close to 0. Okay? So if you look at this formula, since this thing is always between 0 and 1, so the random effect estimate will always drag down or shrink down the fixed effect estimate towards 0. And this is what shrinkage effects mean. And usually when people talk about shrinkage estimate, shrinkage effects, and that's basically something similar to a random effect model like this. And the shrinkage means that in order to gain degrees of freedom or save degrees of freedom to estimate all the effects, so we treat all the effects as an entire distribution. In order to do so, we sacrifice the unbiasedness and we shrink the effect size towards 0. Okay? So I've talked a lot here, and hopefully it is clear to some extent. And now I'm going to use the same simple example as last time to show you the difference between fixed and random effects. It takes that away, go to my terminal window, start R. So I've already saved the reformatted data from last time to the 2 columns for the observation and the groups in the R data format. So I can load, it's called Astro data2.r data. So I have the data 2 from last time again. On the first column, I have the transformed astral measurement for all the measurements, and so 80 individuals observations in total, and the second column is the person index. Okay, so I'm going to quickly refit the fixed and random effects model. First of all, loading the hglm package. It's always slow when you load the lattice package for some reason. It's going to work, I think. Yes. Okay. So let's call it M1. So we quickly refit hglm fixed effect formula is Y1, random is 2.1, it's a bar, it's a factor of person, data is data 2. Okay. And the fixed effect model is basically simply linear regression of Y on the factor of person. Oh, sorry, forgot the data. Should be data 2. Okay. So now from the random effect model, we have the random effect estimate like this. From the fixed value model, we can extract the coefficient estimate like this. But these two sets of five values are not really comparable because, as I mentioned last time, in the fixed value model, the intercept is actually the reference person, in this case person 1, its mean, the mean of person 1. And then we have the remaining 4 persons deviation compared to the first person. And in the random effect estimate from the mixed model, we have the person effects all as the deviation from the overall mean. So if you check the overall mean with the fixed value estimate of the random effect model is 14.17, and the overall mean of theta 2 $y is also the same value, right? So we need to adjust, let's say, the fixed effects estimates, these values, to be comparable to the random effects. So in order to do so, let's call it fixed if, which is, so we adjust the first person first, right? The first person overall mean, the first person's mean is M2 $coef 1. The deviation of this from the overall mean is mean of theta 2 $y. So this gives us the deviation from the overall mean for the first person. And then for the remaining persons, we can simply so we combine a vector. So the remaining coefficient estimate from the LM function is -1, removing the first person. And this estimate plus the deviation for the first person will be the ones for the remaining 4 persons. So now I have a fixed if vector that's comparable to the random effect estimates because all of them are the deviation of each person's mean from the overall mean. And how do I compare those? So let's do a column binding of the fixed effects and the random effects, right? It's like that. So if you check the values, on the left hand side we have the fixed effect estimate, and on the right hand side we have random effect estimate. And you see that all the negative values for the fixed effect is actually a little bit less negative in the random effect estimate. So the positive values are a little bit less positive. Positive values here, less positive. Negative values, less negative. Positive values, less positive. And so this shows you the shrinkage effect, right? So the random effect push or shrink down the fixed effect towards 0. And can we see this or visualize this using a plot? Let's call it PDF because difference is so small we need to properly zoom in. Plot1.pdf, right? Starting a PDF device. Let's plot the fixed effects. Let's reduce the point size a bit. Or probably not necessarily, right? Plot the fixed effects. Let's add some points for the random effects, 1, 2, 5, and $randif. Color is red in this case. And let's add a line for 0 as a reference. So h equal to 0. And close the device, we should have a PDF. As here I see, I'm going to open it, drag it down to this recording area. Okay, so you see that we have 0 here, it's a black line, and we have 3 positive values and 2 negative values. And the blue dots and the red dots are basically, they already overlap with each other. So we don't have so much difference between the fixed and the random effect estimate. And it's not surprising because last time we showed that there are a lot of variance captured by the person effect. So the difference, the variation in the variance in the astral measurements can basically be explained by the difference between different persons. So a lot of information captured by the random effects. The variance component estimate for the random effect is big. So the fraction I showed you just now is close to 1, and that's why we have very similar estimate for the fixed and the random effect estimate. But if we zoom in, let's go to the most positive value here, right? The blue, or sorry, the black dot is the fixed value estimate. The red dot is a random effect estimate, and it's slightly lower than the fixed value estimate. That means it shrink down the positive value towards 0. And if we go to the most negative value, the red dot or point circle is actually above the fixed value estimate, which means in this case it push upwards the negative estimate, so you actually shrink the negative estimate towards 0 as well. So this is what we see for this example, and I'm going to do something else here, because in this case we have a lot of variance captured by the random effects. So the difference between the random and the fixed value is actually not very big, and so the shrinkage effect is not big because the variance component for the random effect is big. What if we simulate something else? Let's simulate a pure noise. R norm. It's 80 individuals, 80 observations, right? So pure noise as our response. So in this case, we wouldn't expect the random effect to capture much variance in this particular response. So if we redo the, let's type it again, right? M1 is hglm fixed y2 1 random bar factor of the same persons, the same data, only we change the response here, right, to be a pure noise. I feed the linear mixed model. We also feed a fixed effect model. So because y2 regress on factor of person from data 2 dataset. Okay. So we are going to do the same thing again, right? So a fixed effect is going to be $2 coefficient, the first person minus the overall mean. In this case, y2 is the overall, is the mean vector for getting the overall mean. And for the remaining is going to be $2 coef, removing the first one, the deviation plus the current deviation. So the fixed effect estimate here, and we have the random effect estimate here. And this time I think the difference will be so obvious that we don't need to zoom in anymore. Let's plot again. If we plot the fixed effect estimate, let's use a color of blue, for instance. We also change the dot to be more clearer. Right, here we have 5 blue dots for the 5 persons. Let's drag this in a bit. Okay. Let's add a black line at 0 now. So 0 here, right? It's a line, it's transparent, you can see it's already there. We add some points for the random effects, which is M1 random. Let's give a red color to it and the same dots. Okay. So now you see it's a very clear shrinkage effect. So all the red values are more close to 0 compared to the blue ones, right? So the positive values are shrinked less positive, negative values are less negative, and so basically the random effect estimates drag down or shrink the fixed value estimate towards 0. And another thing to mention is that the magnitude of shrinkage, so the ratio between the random and fixed value estimate, is actually the same for all the effects. So if the fixed value estimate is big, then it's going to be shrink more magnitudely towards 0. If the effect is small, the shrinkage is a little bit small. So, but the proportion is actually the same. And this is because if I find this document again, right, the ratio here is not a function of the estimate at all. It's only the function of the variance component and the sample size. So for all the effects, they have the same magnitude of shrinkage. And this can also probably be checked by if we do if we use the fixed if or the random effect estimate divided by the fixed value estimate, you have it all the same, which is 0.6253, 52. For all of them, so the magnitude of shrinkage is the same, and the shrinkage should be equal to this ratio. So I will not check here. It should be equal to exactly the same thing from here. Okay, so this is an empirical explanation for the difference between fixed and random effects using a very simple one-way ANOVA model. And so now you should be able to understand what is the difference between fixed and random effects in terms of the magnitude of estimates. So we save degrees of freedom when we fit random effects, but we sacrificed the unbiasedness of the effect estimate. So the estimates are shrunk down towards 0 compared to the true unbiased estimates. Okay, that's it. Thanks for watching.